Good afternoon, everyone. Welcome to the seminar series. I'm Igor Boltas, as you know me by any chance. I'm Bardet here. And it's my great pleasure to host today Professor Bardet from George Washington University. So he does some outstanding research on fluid mechanics and experimentation. We're more this sort of same generation. So we're keeping in touch for the past 10 years at least, and we've been a great pleasure to interact with Philippe in the class today as well. So please welcome Professor Bardet and forward to the talk.
Thank you. You might change your mind after, so don't tap now. Thank you for having me. It's a pleasure to be back in North Carolina. I've been here quite a few times, and I always enjoy coming here. So very quickly, I broke the thing already. Yeah. So let's do that, and then let's take it. There you go. So my lab, in the rough things, we focus mostly on three physical things: multi-phase FSI, fluid spectrum interaction, multi-phase flow, and buoyancy-driven flows. That might be changing in the very near future. This is probably working as of today, but as of tomorrow, within a year, might be completely different. But really, one of the things we do, we like to understand complex phenomenon, and so get new physical insight into complex flows to just for the pleasure of it, and also use that data to validate and develop. Really, we're getting more into the business of helping develop new models, new numerical models. If there is no laser involved, I'm not interested. So, and the laser has to be expensive. And so we have a lot of our specialties, really laser-based diagnostic with lots of high-speed imaging. We like to do the measurement at multi-scale, so we'll see a bit of that today. We like to probe more than one quantity. So that's what we call multiphysics, could be velocity plus temperature, velocity plus chemical species in my system. And one of the motto of the lab is have lasers will travel. We have, I don't know how many lasers I have. I stopped counting at 24. And we take them on the road with us and go instrument facilities that are fairly unique, fairly kind of like industrial environment, bring very sensitive equipment. So a lot of planning goes into taking this and putting it on the road in a truck and going measurement. I'll show you one quick favor of that, but we have done a lot of this and we're doing more and more of that now. And finally, I'm an experimentalist. I like big things. I'm an engineer by nature, so I like building stuff and seeing beautiful stuff. So we have built some fairly unique facility. This is was built on top of a shake table of an earthquake simulator, 6 degrees of freedom shake table. The whole facility was 7 meters tall, 24 feet, 10 feet by 10 feet, 3 meter by 3 meter footprint, 12 tons of steel, stainless steel and acrylic. And we put 6 lasers, 14 cameras on top of that, and had a lot of fun. When you experiment, everything worked. And the next day, the shake table broke. So we got many data, intermediate data set, but the complete data set we've been dreaming about one day, and then shake table decommissioned. So that happened. For example, with the project we did with our collaborator here, we built what I think is the biggest sloshing tank in the world. Its size matters when you do a wave impact because you can entrain air and then your flow becomes compressible. So the bigger your waves, the more compressibility effect you're going to have actually in your bubbly flow. When you're at a wave impact, you have shock waves, your speed of sound drops down to meters per second. So even though your flow, your sloshing tank is very slow, you have shock waves traveling at Mach 2, Mach 3 inside the system. So very fascinating physics. And the bigger your tank, the more of this you're going to capture. And many other things we have been doing throughout the years. So quickly, what is the George Washington University? It's named after the first president. It was created by an act of Congress in 1821, so it's a fairly old university by US standards, and we're in the middle of it all. The White House, of course, you recognize is right here, and so the campus is 5-6 short blocks from the White House, next to many international organizations and exciting things. So one thing you might have noticed lately, politically, Washington has been very chaotic and turbulent. And that's an introduction to my research, which is on turbulence. But as we learned from Orson Welles, turbulence is a good thing. So that's our introduction to turbulence, okay? So with that being said, now let's jump into a bit of the meat of what we're doing. So experimental thermal hydraulics or numerical thermal hydraulics is a fascinating field of research. This is what got me excited into doing research. It's hard. It's really hard. We could argue it might be the most complex field of engineering if you want to be very precise today. I don't think maybe with naval hydrodynamics that might be the most too complex things you do if you really want to capture understand all the small physics. So it's turbulent almost always. It's many times multi-phase flow, except if you're smart and look into advanced reactors where you remove the production of a two-phase, right, like molten salt or gas-cooled reactors. You have heat transfer, obviously. That's how you take care of removing the heat from your reactor. You sometimes have mass transfer. Sometimes you don't want it, but it's still there. And it's also multi-scale. Your smaller scale of turbulence happening at micrometer, and that's happening in the plant with kilometers of pipes inside. So can we really understand and model all of this? It's very complicated. So we cannot really simulate this from first principle per se. So we have to use model. And the model, as an experimentalist who doesn't do model or modeling, will tell you is as good as the data that you have. And the data could come from two sources, come from high fidelity simulation, and Igor here does some of that, or highly resolved experiments. And also you need your developer, the person developing the model, needs to have good physical insights. And in fact, you see many times some of the big name developers like Philippe M, for example, who has developed one of the most famous Reynolds average Navier-Stokes models for CFD, has to go do experiments himself because he was missing some of the insight he had to go in the lab and get the data to get a feel for what was going on. And that inspired him to create some closure terms in his very famous models. So with that in mind, I'm always trying to, when I conceive of an experiment, think about the wisdom pyramid. I get familiar with this, right? When I take data in my lab, I'm sitting at the bottom here, so my raw data, temperature versus time. Then I do a bit of a regression to my data, find the mean, the RMS, from that I extract information. And then from that, coming from multiple data sets, some smarter people than me develop some models. And that's what the knowledge steps. And then really smart people know when to use the model and when not to use them. And that's the wisdom thing. Okay, so one example of this, we can do a nice analysis of tomatoes. We're going to realize a tomato is a fruit. That's knowledge. Wisdom is not to put them in a fruit salad. So that's the things. So here, one of the motivations we had recently in the lab was to study the Walsh spread. So I'm sorry, I'm going to go a little bit deep, not too deep, but a little bit into wall-bonded turbulence. That's going to help illustrate what we're trying to do. It's still going to be a fairly high picture, but if I'm going too fast, ask me and I will slow down and try to clarify things. We'll come back to that graph at the end of the talk as well. But so the Walsh stress is really the velocity gradient that you have at your wall. And if your fluid is Newtonian, that's a type of fluid, which is water, you will have that the friction, the drag on your surface is proportional to this velocity gradient in the wall normal direction. And this constant of proportionality is the viscosity of the fluid. Okay? This quantity happens at a scale in a turbulent flow at this viscous wall unit L sub nu. So you're going to see L nu coming up many times in my talk here. And what we use and what we did is with this viscous wall unit, we use it to normalize my length scales. So here, X in everything I'm going to do is going to be the axis of the flow, X for axis. Okay. The wall normal direction, the direction away from the wall is going to be Y. So X is with the flow, Y is away from the flow, and Z the direction we don't care. It's the span-wise directions out of plane. Okay, so everything you're going to see is going to be in an XY coordinate system. So for us, what we're going to try to resolve is the projection of this instantaneous wall shear stress in the X direction along the axis of the flow. So there's going to be du. U is the X component of the velocity, the axial component of the velocity, dy. And at Y equals 0 at the wall location. The wall is always at 0 at Y equals 0. Okay. So we're going to normalize in what we call inner unit. And we're going to introduce this Y plus dimensionless unit, which is my wall normal direction normalized by this viscous length scale. Now, this viscous length scale is very small. If I work in the PWR, prototypical conditions, so 150 bar, 300 C water, my Reynolds number based on the hydraulic diameter, hopefully you know that, is on the order of 500,000. And my viscous flow unit is 1 micrometer. Your hair thickness, for those of you who still have hair, yes, I'm ahead of all of you guys, almost, is about 100 micrometers. So you want to be resolving things to really capture this wall shear stress properly. You want to have a resolution on the order of the micrometer. If I do measurement in my lab, not high pressure, not high temperature, that relaxes a bit my requirement. My Reynolds number is way less, 1 order of magnitude less, but my viscous length scale is 10 micrometer. So if I look into this distribution of scales in my turbulent flow, in the first, what we call 5 wall unit, we have what is called the viscous sublayer. So in this first 5 wall unit, on average, my velocity profile is linear. So that means as I go in the distance away from the wall, it's nice linear slope on average. We'll come back to that in a second. So ideally, I want to be working in the first 50 micrometers near the wall where my flow is nicely behaved. Once I go above, outside of this viscous sublayer, it becomes a big mess. So if I want to measure wall shear stress, I need to decide, well, what kind of resolution I need to have and how do I do that measurement? So that's really 2 questions we have to answer experimentally to develop the tool. So here, delta, when I use the symbol delta, I'm talking about precision, accuracy. Okay, so my sensing length, to some extent, is going to be related to the accuracy of my measurement. That's why I'm going to give it the symbol delta. The sensing length is going to be the characteristic length scale of my probe to do my measurement. So on the mean, going back to some multiple. So the black line, so here you have on the x-axis your wall normal direction normalized by this viscous wall units, y plus. And in the vertical directions, we have normalized the velocity by the viscous velocity scale, and we give it U plus symbol as well. So on the mean, within the first 5 wall units, that's the red line here, we have that U plus equal Y plus. We have this nice linear profile. On the instantaneous, that's the collection of black line you see here. I'm not linear. And you can see the flow to some extent looks sometimes concave, sometimes convex, depending on what I am. And that can induce that many diagnostics have been based on relying on the fact that U plus equal Y plus, my velocity profile is linear at the wall. And in fact, they have used this. For example, if I do this individual measurements here, I'm at 3 wall units from my system, that's the blue dot, then interpolate linearly to the wall, or the velocity should go to 0 to satisfy your no-slip condition. Okay, if you do that, you will see that in most cases your flow is slightly concave, and so you will have a tendency to really underestimate your asymptotic at the wall, which is the blue line. So by basing yourself at a fixed height in this viscous sublayer and doing a velocity measurement at this one, extrapolating linearly to the wall, you're going to underestimate your skin frictions, your wall shear stress, your drag on your viscous drag on your blade. Okay, so many diagnostics are really relying on this. And so what does that mean? If we interrogate DNS databases that we trust fairly well, the well-resolved data, is that my error on my mean velocity, which is vertical axis that is here in percentage error, and on the horizontal axis is the position of my probe in viscous wall units. So for example, if I put a probe at 5 wall units and I extrapolate linearly to the wall, I will underestimate my wall shear stress by about 5%. That's assuming I have a perfect probe. I do not do any special filtering or temporal filtering of my data. We'll come back to that later. So with a perfect sensor, doing this linear interpolation, which is really hard measurements to do. Remember, we want to be at 50 micrometers from the wall, half of your hair thickness. I need to put my probe there. That's really hard to run this in a turbulent flow where your probe might be moving and etc. So that's not a trivial measurement. And if everything is perfect, we'll underestimate by 5%. If I look into the fluctuations of the turbulence, the RMS of this wall shear stress, if I put myself something at 5 wall units here, I will misrepresent my fluctuation. It's a dimension, it's a positive quantity, the RMS by 20%. So you can do very quickly simple mistakes you're gonna miss your physics by doing these measurements. Now, the good news for you, if you guys are good engineers, you might have noticed, so here what we have is 3 trends, 3 different Reynolds number. I should have split 4 different Reynolds number. And what you can see is that as a function of Reynolds number, they have, independently of Reynolds number, they have the same trend. So if I'm working in a well-known geometry, I can do a correction factor to correct for this effect. Okay, so that's a saving grace that we have. And so this is where we start getting into diagnostic philosophy, where we see that many times people develop a probe, they think it works, 5 years later they realize, hey, shit, I'm underestimating by 5%, but I can do a correction factor. So now I'm safe. And so in some of the techniques that have been used to measure water stress, they use 5 different corrections to the things to extrapolate what they think is the right result. I don't like to do those correction factors. I want something that is multi-rate. Because who knows if we're missing one of those things, okay? So, and then if I also work in a geometry that is now more complex, like this is for a simple 2D flow, a channel flow, nicely behaved turbulent. If I work on a more complex geometry, like a fuel bundle, for example, or going for a spacer wheel or one knot, I don't know what is the correction I need to use. So I might be using that correction, but I might introduce another mistake that I'm not controlling. So we want to be careful with this. So the other effect coming into play is this. So that's we answered the first question. Where do I need to put my probe with respect to the wall? Ideally want to be at the wall, right? If I'm a bit away from the wall and extrapolate, I will make a mistake. The other question is, what is my sensing length? How does that filter my data? So the base measurements, in fact, all the knowledge we have on turbulence, or 99.9%, is coming from 1930s, 20s technology, which is hot wire. Hot wire is a very thin wire, typically 1 or 2 micrometer in diameter, so much smaller than your hair. And you are sending a constant current through it, or you're keeping the temperature constant, the PID controller on your wire, and you're measuring the heat transfer induced by the flow across your wire. Okay, so for this to work properly, you need to have a laminar flow above your wire. So if your wire is too big, if your Reynolds number based on the wire diameter is more than 45, you will start having separations behind your wire will start oscillating, and that's going to completely change your Nusselt number correlation and your measurement of the velocity. So you want to be very careful in selecting your wire such that the scale of your wire, the local Reynolds number, is in agreement with how the wire should be used. Okay, but on the hot wire, you typically have an aspect ratio. It's typically 100 times longer than it is in diameter. So what you do is that you're going to be averaging your measurements of the velocity along the length of the wire. What matters is not the diameter. The diameter matters for not having the right heat transfer across the wire, but really you average your data, especially along the length of the wire. Currently, if you are in a Princeton, you can make those hot wires down to 30 micrometer. They work only in gases, and they break all the time. 60 micrometers are a bit more reliable, but only work in gases. If I want a commercially available system in water, I have to go on the order of a few hundreds of micrometers, a few times your hair thickness. Remember, my length scale, my smallest scale of turbulence I want to resolve is on the order of 10 micrometers or down to 1 micrometer in prototypical conditions. So here you're going to be filtering your data significantly and removing some information. If you want to have a high-speed turbulent process, so lots of fluctuations, by having a long wire, a long sensing length, I'm applying a low-pass filter to my data. So I'm removing some high-frequency content in my measurements, which might make me miss the mean value as well, not just the RMS, but also the mean. Another technique that is very popular, and that's why I got my PhD in, is PIV, particle image velocimetry. Very simply, it's very crude. It works fantastic. You put small particles in your flow, dust, small glass beads or diamond, silver-coated glass beads to get nice and shiny, and you cut a cross-section of your flow with a laser plane. Okay. As your particle goes through the laser plane, they emit a flash. They scatter light because they're highly reflective. Coming with the camera, I can record those flashes. If I take 2 images close in time, I can correlate the displacement of a patch of particle from one frame to the next frame. And we have computer algorithms that do that automatically. And so with this, I can find my displacement. Knowing the timing between the 2 frames, I know the velocity. I can also be smart and do time resolved measurements and measure acceleration. So if I measure acceleration in your Navier-Stokes equations, I have resolved all the terms minus the pressure. So I can inverse doing a Poisson, solving a Poisson equation like you will do in CFD and reconstruct the pressure from my time resolved PIV measurement. So now with PIV, we're extremely powerful. Okay, but my sensing length is typically on the order of 100 micrometer if you're really good, but more like 1 millimeter if you use a commercially available system, which is what most people use. So when you average your data, you're not averaging in PIV over a length of 100 micrometer, but over a volume of 100 micrometer cubed. So even a larger volume than what you have for hot wire. So that's creating even more filtering of your data, and you're missing more and more of your turbulent spectra or energy that you want to capture. And finally, with MTV, this is where we got started. What you can see very nicely with MTV, here we are creating a first line of tracer. I'm going to explain to you how we do that in a couple of slides. And my next frame looks like this continuous signal that is here. So if I want to measure gradients of velocity, I have direct access to my slope here, to my gradients, by looking at my data. So it's very visual. And previously in MTV, the resolution was just really, really bad, even worse than PID. We made some progress in the lab, and now we can do this with a sensing length on the order of 10 micrometer, which is the scale I want to be at for resolving my high Reynolds number flow in industrial application. And I'm going to show you how we did this. Let's keep that in the interest of time. So in thermal hydraulics, which frustrates me and quite a bit, most of the knowledge we have on flow in rod bundles is really from the 1970s. Or a polyresolved experiment from the 1990s. Okay, the experiments were really hard, really state of the art back then. But if you look into the scales, they are way off and they're missing a lot of information. The data are not statistically converged. They are very coarse, so they're filtering those quantities that we want to capture. And they have to apply a lot of correction factors to the different techniques they're using. So we could spend 30 minutes deconstructing this. That's the first thing you do when you join my lab. I won't do it here in the interest of time, but we have to be aware that most of the models we have are based on very, very old dataset, 1976. I do not believe there is anybody born after 1979 in the room. Is that correct? I might be the oldest person here, 1979. So those data predates me and predates anybody in the room, and they are very, very cool. So how do we measure velocity? There are many ways of doing it. The philosophy in my lab is that we are not married to one technique. Some people come to you, say, I want to measure this. Oh, I have PIV, I can do it for you. That's not the approach we have. The approach we have is like, well, let's understand your process. What is the resolution you need? What physical process do you have at play? What can we exploit naturally in your flow to find the right technique for you? Okay. As I said, so we can do measurements of velocity, velocity of fluid in 3 different ways, using probes, so electronics if you want, using optical techniques, lasers, or using a sonic system, your ultrasonic system. So I'm not going to go into the whole list, but the hot wire, which is where we learn hot film, that's where we learn the most from in turbulent flow, and that's really all technology, and that's right here. Most of the knowledge is still coming from here and is still being produced today from those techniques. So even though they're still old school, they are still the best today. If I use optical technique, we can base ourselves on the Doppler effect. You guys probably know what is Doppler effect. You can be smart about it and be very, very precise with those measurements. Not my specialty. I'm more specialized in time-of-flight techniques using particle techniques of PIV, which I just described earlier. And the big effort we did was on MCV, which I'm going to describe to you now. So when we were asked to do this, my program manager likes to say, I want a moonshot. Like, propose something crazy. And if you go to him, he's like, not crazy enough. So he wanted something crazy. So I was like, hey, I'm going to measure wall shear stress directly, which has never been done optically. It's going to be extremely precise. We're going to have the right spatial resolution. We're going to be time resolved. And we can do this ideally in a volume. And maybe we can also resolve the large structural descent. And it's like, that's crazy. Let's do it. Okay, so about 1.5 million later, here's what we have to do. Okay. So what is MTV? MTV, it's a 2-laser system. We have a first laser, which is in purple, which we call the right laser. So the right laser, in our case, in water, it's a UV pulse, 355 nanometer, very short pulse, 10 nanoseconds. Some people will tell you that's an eternity. And then what we do, we use that to excite, to create some tracers in our flow. And then we come with the second laser, what we call a read laser, which is green in our case, which is a visible laser. So 527 nanometer here, 522, whatever the details. And what we do fluorescence on the tracers, on the molecular tracers we created with the first laser. So we're going to seed our flow with some tracers. In water, we use rhodamine dye or fluorescein or some kind of a fluorescent dye, laser dye that makes your markers shiny and fluorescence. Same thing we put in water. In gases, we work a lot with N2O, laughing gas. So my students love that experiment because everybody is super euphoric in the lab when we want it. We use water vapor, H2O, ozone, oxygen, all the different tracers we can use that are naturally in your air, so you don't have to do anything to see the flow. Okay. So that's what I'm saying, by trying to exploit what is at play here to create that, to find a way to do the measurements. And then we come and do a second image of fluorescence. So we fire the read laser a second time, and instead of time delta T later, again, delta resolution by time interval. And we can see the initial, where my first purple laser, the white laser went through, I created this line of radicals of tracers behind, and I visualize them in the first read pulse. And with the second read pulse, I see the advection of this pattern. By doing a correlation between the two, I can reconstruct my velocity profile fairly precisely. Okay, and so my velocity in the end is relative to my displacement in pixel divided by the time interval between the two images and the magnification of my image. So it's spatially continuous, so we can potentially resolve gradients. But historically, pardon my French, the resolution sucked in spatial term, temporal term, and we had to use very, very expensive lasers. So we're like, hey, can we do this using traditional lasers? So the first thing we had to address is how can we create very fine pattern? The state of the art before was the best people that had ever done was beamlight about 100 micrometer on the size of the diameter of your hair, which is too coarse to do what we want. And they were fairly sparse, 0.5 millimeter between beamlights. So fairly crude, but yet back in the days in the 1990s, they still managed to capture the velocity gradients here at the wall. You have a wall at the bottom here, and they get the gradient directly in this low Reynolds number turbulent boundary layer. Okay, so that's what inspired me to invest in this. Like, if I could redo the same measurement at much smaller scale, I will have what I need to make it work. So how did we do it? We got a bit of luck. As usual, it's me telling a student to do something that was wrong, and the student spending weeks and weeks losing his mind. He finally go in the lab, realized that nothing works. And I told him, you have 2 weeks to give a seminar to the group and explain to us what's going on. And that person responds to stress. And in 2 weeks, he gave the best student presentation I've seen. I was on the edge of my seat, and I was like, we have it. We have exactly what we've been looking for. So the principle is very simple. You're starting with the distributed light sources. If you have like a Fresnel's slot to do your final third diffraction, in our case, we create those points with a lenslet array. So we're focusing the light at a couple of regular spacing. And what you find after a distance called Z-sub, which we call the Talbot distance, which is called the Talbot distance, we are recreating this initial pattern. Now that distance is relative to your initial velocity, P0 square, to the square root, and the wavelength lambda of your laser. So this is quite remarkable. In my case, I start with a lenslet array, 300 micrometer periodicity. And if I put myself a quarter of a meter away, my Z sub t distance, I recover the initial pattern. If I put myself 2 Z sub t, half a meter away, I recover exactly the same thing. 3 Z sub t, I recover the pattern again. I told that to a friend of mine who does optics for a living. He's like, that's true, everybody knows the Talbot effect. I was like, never heard of it. It took us a while to figure it out. So depending on where we come from, it might be easier. And so, but what is very remarkable is I put myself at intermediate distance. So a quarter of this, now I will have 4 times the periodicity of my initial pattern. If I put myself at 3/4, I still have 4 times, or 5/4, or 7/4. I will have 4 times my initial periodicity. And at the same time, my beam gets a bit smaller. So now I have a very flexible way of creating pattern of any size I want. And in fact, it's a fractal pattern that you have here. So by controlling my lenslet array and putting it at a different distance from my field of view, I can really go down to, in this particular case, beamlight of 17 micrometer in diameter with a periodicity of 40 micrometer. We have done to 7.5, that's the smallest we have done. So that's really a very, very flexible tool. To simplify, the way we were doing it before, people were focusing their lenslet array and doing measurement at this plane right here. And this is the mistake I told my student to do. I didn't understood the focal length of the lenslet array I had bought. I thought they were a meter long, and they were already 8 millimeter long. So I was like, yeah, put yourself a meter away, and you should recover, your thing should be perfect. And it was a complete disaster, and because we were seeing this. So once we understood it, we're like, yeah, I was lucky. So anyway, so that's that. And so then what you can do, you can combine those beams and do a grid. So you can do multi-line, you can do a grid. You can also come with a spherical lenslet array. So instead of being a set of cylindrical lenslet array, it's now a matrix, 2x2 matrix, and that can give you a 3D pattern that you can create in your flow of any size you want. Just a matter of controlling the distance between your MLA, your micro lens array, and your imaging plane. Okay, so how do we do MTV in water? So this is go back to the moonshot. I was approached by the Navy to instrument the thing. As I said, I like big things. And I'd been trying for 8 years to get into that facility. So when they came to me, I was like, whatever I need to do, I'll do it. And so this is actually for the little history. This was built in the forge where they built most of the nuclear reactors in the US. When the forge was decommissioned after the US started building nuclear reactors in the late 80s, the Navy needed a big solution to design their next generation propellers for the next generation submarine. Okay, and the senator in charge of appropriation told them you can have it as long as it's in Memphis, Tennessee, because it is from Memphis, Tennessee. So they built this. It's owned by a facility in Washington, D.C., but they have to take the plane to go to Memphis to run experiments there. So it's a logistical nightmare. And when they decommissioned that whole forge, the deal they had is that the last job the quartermasters were going to do there was to build that facility, fabricate all the parts and build it inside, and then donate the building to the Navy. Okay, so to put an idea of scale, you have people here, right? This whole thing is an ASME Code 3 pressure vessel, stainless steel. It's about 300 feet long and 80 feet tall. So about 100 meters long by 20 meters tall. When this was built, it took half of the US production of stainless steel of 1991. There was a world shortage of stainless steel because of the fabrication of that facility. So that's a massive thing. This whole thing is vibration isolated, sitting on huge slabs of concrete that are floated below the whole thing. Imagine the weight and imagine the kind of force you have under this thing. The engineering of this is a masterpiece. And the test section is 10 feet by 10 feet, 3 meters by 3 meters. And you are moving waters at 20 meters per second. So it's a higher flow than you have in the hot leg, return leg of your PWR, and it's much larger diameter. So the pump for this is 24 megawatts. That's just the pump. You have all the auxiliary system to give the temperature control and keep all of this. There is not enough electricity in Memphis in the summer because of AC to run the facility. So you can only run it when it's not too hot or not too cold. So this is really a marvel of engineering. And you go inside and it's just like, this is stainless steel. This is crazy. I mean, this is the walls are like 2-inch thick stainless steel. Right? So it's a baby. It's a big baby, and it can go to vacuum to high pressure. So what we're going to do in this, we are going to test this generic geometry. This is a prolet spheroid, so like a football but more elongated. And we are going to deploy this MTV technique I've been presenting to you, putting everything inside this very confined specimen. So a lot of engineering is going on now into making everything very miniature, very robust. Everything is computer controlled, remotely controlled, so we can put it into this facility and take measurements and readjust things on the fly without shutting down the facility. To put things in perspective, 1 day of runtime in that facility is 1 year of graduate student salary. Okay, so if the graduate students forgot to turn on a switch before we close the thing, he's going to have a lot of people yelling at him or her for making that mistake. So there is no mistake.
You're going to graduate 1 year early, right?
He's not gonna graduate. He's gonna be he or she is gonna be on the job market right away. So so this is the kind of running this thing is really high demanding, and so we have a lot of pressure on us to make sure everything has been troubleshooted and tried 20 times. It's not going to spec pretty much because of the cost of that facility. Okay, so it's a very exciting project. So now I discussed how we could do very fine pattern in MTV. The other issue we had, and we had solved that issue before we got the grant to go instrument this, was to how do we create pattern that we can go to high speed. So there are 3 ways of doing MTVs. I'm not gonna describe them in detail. The main conclusion is they are very hard to do. Their response time is very slow, and you need very expensive lasers. So the big thing we did, and here it's me again making a mistake in the lab, we thought we were smarter than our little colleagues, by using what we call a cage dye. So a cage dye is my fluorescent dye, my rhodamine dye I put in my water. And people that do biomedical engineering to track, they tag protein cells to which they give cancer with those dyes. And they can, and they put a cage to it, another molecule that prevents the dye from fluorescing. So when they go to a particular spot, they zap them with the UV laser and activate those proteins that they can then follow as the cell is growing or whatnot. So I knew a colleague was doing this. I was like, hey, I found a way, because they were using green lasers to do this. I was like, if I use that thing and I can dissolve it in water, I have a way of doing the measurements in a very easy manner, using traditional lasers that are in my lab. And so we did it. We bought the fluid, we bought the thing. It took us a while to understand how to dissolve it in the right concentration and whatnot. And the thing that broke my heart is that it took 30 milliseconds from the time you fire your UV laser to encage the dye till you can finally do interrogation of your dye. No, I didn't mention that, but the time scale we're looking into in our measurements is tens of microseconds. So 30 milliseconds, 1,000 times slow, it's a non-go. And the reason we couldn't see the signal initially is because we were like uncaging the dye and looking for the signal a few microseconds after, and there was nothing. There was nothing to look because it took a long time for the molecule to recover from the excitation and start fluorescing. And I got annoyed, and I turned the laser. I cranked it to 11, and the student was like, "Ah, don't do that." So I turned it to the max, and here is what happened. We started burning the dye that would dissolve in the flow. I was like, "Hey, that's your MTV signal. We have a signal." He was like, "But that's not the right signal." I'm like, "It's a signal." So it took us a bit of time to understand what we were doing and realize that this is really the scheme. And that's what we started developing. So we went into understanding the spectroscopy of rhodamine dye in more detail. Without going into too much detail, you have two peaks of absorption of your dye, one in the green, where you have a lot of laser at the wavelength, and another secondary peak in the UV, where you have a lot of lasers near that wavelength as well. In a nutshell, what you have, we went back into chemistry, fluorescence kinetics papers to really understand how these things works. We realized we could simplify this kinetic model significantly from a 5-level to a 3-level, neglecting a bunch of terms. And in the end, here's what we found. The rhodamine dye, we know if I excite it with the UV, with a green laser, is extremely robust. It will not get destroyed. I can excite it millions of times, it will still work. If I come with a UV laser, it takes about 4,000 times less irradiance, but almost 5 orders of magnitude less irradiance or energy per pulse, if you want, to break down that dye with my UV laser. So historically, people have been using this dye with green laser because it's very robust. Once we move to a UV laser, we can destroy it very, very quickly. And so that was really the big benefit of that analysis. And that's really made us understand that we don't need to turn the laser to 11. My lasers are typically a joule per pulse, really big lasers. And to make it work, we need to be at microjoules per pulse. So that was a big headache we had in operating the laser. You start with this massive laser, and really what you should be using is very small stuff. And so we had to bleach 99.99% of the dyes, get rid of it, to really make the technique work properly. So that was something to understand as well, is to reduce the power to increase the signal to noise ratio. And that was an expensive process. So in the end, we had to calibrate the technique. So we built this turbulent channel flow with previous slides to the turbulence. Fairly well known, DNS can go higher than what you can hope to do in an experiment. So we're not trying to understand physics here. We're just trying to have a tool to calibrate our instruments against DNS dataset that are fairly well established. And again, will beat us any day in a Reynolds number. So the important thing for me is not to go to high Reynolds number. This is my friction Reynolds number, which is here, but it's to go to small viscous length scale, my LNU, to see if I can capture the right physics with my small beam. And in the end, this is what we have here. My viscous wall unit is about 12 micrometer. And you see here, every 10 frames, I'm writing my pattern. So I see my multi-line that are vertical. My wall is horizontal at the bottom here. This vertical line here is my first 10 wall units. And you can see in the right after the pattern is written, your beam being deflected, and you get your nice gradient at the wall. Now, it is not linear on the instantaneous, so we have to be a bit careful how we interrogate this and not just do linear interpolation. So a lot of work is going on now in doing this. The important thing here is my sensing length is really my beam diameter, which is in particular case is 25 micrometer, 2 viscous volume. Is that sufficient? People that do DNS will tell you yes. Typically, when people do a DNS, their mesh size in the streamwise and spanwise direction is typically 5 to 10 wall units. Here we are at 2 wall units, so we're over-resolved compared to DNS simulation. In the wall normal direction, which is what matters to capture this non-linearity in my velocity at the wall, we're on the order of 2 micrometer, so 1/5 of my wall units. We can play with the parameters, increase the beam periodicity. Here we have intermediate type plane, so 4 times more beam in this case, different magnification, and you can see your nice gradient, and you can capture some large flow features at the same time. And really, so here are some snapshots of that. And really the cool stuff is this. Here we are interrogating the laser slightly differently, and now you get access to a nice features, or you see some large scale flow features coupled with your wall at your gradient at the wall. And we're in the process now understanding what's going on with this data. But here, instead of firing the right laser once and doing multiple read, I'm doing one read and I write a lot. I write 5 times and I do one read. So we have multiple black lines that are highly spaced. And what you can see here, we can see some effect of stretching. For example, here my lines in this particular region are being more stretched, it's vortex stretching. In some other region of my flow, the lines are being compressed. Also in the vortices, it's a very nice way of marking the vortices near the wall. So we were expecting to see all vortices that way, and in fact, some rotating in the other way, which is counterintuitive with what we understand from vorticity transfer from the wall to the bulk of the flow, and even larger features. So here you're looking at the first 200 wall units in your system. So we really see an injections of like this vortex ring here, most likely, into the bulk of the flow. So transfer of kinetic energy from the wall to the larger region of your flow. So there is a lot of physics to be to go after here. We are just starting to scratch the surface of this. We're collaborating with teams that do DNS to see if they identify similar structures in their simulations. This is very rich data set. A lot of work needs to be done with this. So how accurate are we? If I compare myself to my delta P measurements, that's what I call my wall shear stress on my measuring the delta P along my channel. That's the traditional way of doing these things. For my measurements, I'm within 1% on the mean. So I'm pretty good on the mean. On the instantaneous, here we analyze 120,000 frames to have some kind of descent statistics, still not enough. But we are on the instantaneous, we are capturing the skewness and the right RMS that you expect in turbulent channel flow, and also the trends, the fat tails, which are really 1, 2, 3 orders of magnitude from your peak. We are also capturing the right trends. Now, if I go to a smaller wall unit, this is the data set that we have here. So higher Reynolds number, my wall unit is a bit smaller. We're having issue capturing the high extreme event. That has to do not with the technique, it has to do with the lasers. We have too much of spatial filtering. The laser repetition rate was limited here. And so we are missing some of the most positive events. Okay, now to bring that back to thermal hydraulics, your correlations, I believe, for DNB or CHF or whatnot, do not take into account any of the fluctuation, it's just based on the mean, because that's the only quantity we can measure. But if you look into your events, you're highly skewed toward, this has been normalized by the mean value, you have a lot of extreme positive events taking place, which in my opinion, should have a huge effect on this correlation. And again, it does not exist because there is not there to correlate them to. And I think I would like us to revisit this as a community a little bit. So I have a few more minutes. I'm going to go very quick here. The other questions we had is, can we do this volumetrically? Everything I showed you so far was in a plane. Yes, fairly boring. Fairly boring. That was quite an accomplishment, in my opinion, to get to that. But can we do this volumetrically? So the idea I had, as the benefit of young kids, you don't sleep at night with the screen all night. So you have time to think. And so the idea was like, hey, can I do a confocal microscope? I guess familiar with the confocal microscope? You come with a microscope objective, which has a very narrow depth of focus. So you can optically section your transparent specimen by moving your objective or your specimen with respect to the objective. And so you're going to isolate optically different layers through your specimen, let's say, by moving the objective. Okay, very standard techniques, very well established, but it's slow. Okay, so the idea is I could have moved my objective and capture different plane in my system. So if I could write my pattern, an array of beamlet, which I showed you we know how to do, and if I could move my objective at different depth, I should be able to reconstruct the 3D displacement of those patterns. Okay, so how do we? So the principle is this: I have my surface. My initial beams are the black beam, and I will ideally optically section my flow by moving my system. And so my initial beams are the black beam that are straight, and then the beams are being deflected, advected by the flow. That's what we see in blue. And so if I could do several layers like this, I could reconstruct my velocity gradients or my turbulence at the wall. Okay, so we are like, okay, can we do it? So skipping about microscopy, which is very exciting in the interest of time, there was this company that came out where you can have this adaptive optics microscope, where you can zoom from 0 to infinity, which in your microscope is like 200 micrometer, but with very high spectral resolution at 70 kilohertz. So I could do a whole scan at very high speed. We also have cameras that are now available that might work fairly well at that speed. But remember, I'm at 70 kilohertz, it's a sine wave, right? The period of 70 kilohertz. So if I want multiple planes, my camera has to be at several times. If I want 5 planes, I have to be at 10 times that up and down, right? So those cameras can almost do it now. That costs, by the way, over 200K. That's fairly inexpensive in comparison. So that's what we proposed to sponsor initially. And we're about to start it. I heard the students, I'm like, man, that's just a waste. We couldn't do better. So we looked into plane optic imaging. Plane optic imaging is a 3D imaging. I don't know if you're familiar with this. What you do behind your main camera. So if I take a regular camera, I take my camera lens and I get 2 objects, so 2 balls. And when I take an image, it's a flat image. I lose depth information. Okay, but I have perspective information. So if I put a macro lens array behind this primary lens, it allows me to look into my object through different perspectives. And so now I see the relative displacement of the 2 spheres with respect to each other due to the different perspective. So coming from a single camera, but in a single lens, introducing this another MLA, another macro lens array. So here we're using MLAs to create the pattern and also MLAs to do 3D imaging. So 2 types of MLAs. I can really reconstruct my scene in 3D from a fairly compact system. So there are 3 flavors of plane optic. The initial one, of course, is French from 1908. In 1908, there was no computing power to do it, so the patent was filled, and that was the end of it. In 1990, a professor at MIT dusted this off. Computers were not there yet, died again. In early 2000, a professor at Stanford who created Google Maps after, and all of this. So he got hired from Stanford to be the head of anything 3D imaging for Google. Probably makes a lot of money doing this. Revisited this and recreating something that looks fairly promising. Okay. The problem of this, we did a very thorough analysis of that system. He was not going to give us the resolution we want. It was too costly. So we gave up on it. Then there was a commercial system that came out really a couple of years after this 1.0 approach, 2.0. Unfortunately, the person that has the idea got a patent and blocked all development to create a company that he oversells you the things for a lot of money. Okay, so it's a nice turnkey system. You don't control the software. You have no idea how the reconstruction works. And because it's behind a black box and it's patented, there is no scientific community of users. So you're stuck with what you have. So he had promised us the moon. Even though he was German, he was nice and gave us a demo camera to play for 6 months. We tried very hard. We got the data. The information is there. I couldn't get into the software to modify, to make it work for what I wanted. And he refused to give us access to the software. So we gave up on this. And we found another technique after 6 months, which we identified initially, that is now like more open source. There is no patent behind, and you can reconstruct, build your own system. We found some initial source code available on GitHub that we started taking and modifying. So this is really the effort we did. It's called Fourier integral microscopy. It's fantastic. It's really fun. So the principle of Fourier integral microscopy, you have your microscope objective that is here. And in the aperture stop of your microscope. So remember in your camera, you have the f-stop, the diaphragm you can close to change your depth of field or how much light you get into your system. In your microscope objective, we have also this aperture stop. It's called the Fourier plane in microscope. Just same thing, different, yes, exactly the same, but that's what it is. So if you put your micro lens array in this thing, that will give you different perspective directly through your microscope objective. And that's how you can get to very high, strong perspective in your microscope. So in a microscope, you're really looking with a very high numerical aperture, with a from very wide angle into your specimen. So here I really have a lot of different angularity from which to look at my spaces from, which give me a very good resolution in depth. So that's really the benefit of the technique compared to the other approaches. So that's the principle. In practice, you have other optics in between, because in most cases you do not have physical access to this aperture or stop, to this Fourier plane. So you create a relay lens system to project it further behind. Okay. So that's how it looks like. Without going into detail of the design of it, but because I could spend quite a bit of time, but it's kind of fun. Here is the view you have. So your view on your camera is, this is a view through each of the microlens. So here I'm looking almost down the axis of the beams actuated that are written normal to my wall, right? I have my surface and my beams, it's a forest, if you want, of beams, normal to the wall. Here, I'm looking along the axis of this beam from my central view. On the side views here, I'm looking at the beams now from an angle, right? And you see this perspective along the 6 views that are here, that are changing with how I'm looking at my beams. So you really see the strong angularity of the system. In this particular case, we have, so this is the central beam here, so the central lens array, so the central micro lens, I've got the central view, which is aligned with my and then perspective from it. So what I have really is 13 mini cameras built into one system. The huge benefit of that technique as well, to the strong angularity, I do not need very high resolution camera. The other plenty approach, you need 20 approaches, you need a 25, 30, 40 megapixel camera. They exist, they are very inexpensive, but they don't go fast, and I want to go fast. So here I can get away with a 1 megapixel camera, and I can go at 75 kilohertz. I can go fast. I can more than run with this. So now I have access to a tool that can do the 3D at high speed. This is really big benefit of this approach. So on the left here, you have your t=0 image, and on the right, you see now with flow. So you see a little bit the beams dancing, right? So it's a sequence of multiple views taken with flow. And the reconstruction we get, let's keep all of this in the interest of time. The reconstruction we get, this is your t=0 image. You get those beams that are normal to your surface. Color marks depth here. The spacing between the beam is about 300 micrometer, and the beam diameter is about 30 micrometer. So we're really pretty much at the same resolution I had before in my plane, except now I'm volumetric. And on the right-hand side, it's a sequence of 10 images with flow, and we're going to be changing the perspective view when we do the reconstruction, so you can have a better feel of what the pattern look like. Again, I'm working the spacing between beams is 3 times your hair thickness, and each beam is a third of your hair thickness. This is the higher filtering length we have is on the same order than you have with the best hot wire that only works in gas. Here we make it work in water. In water, there's nothing that comes into that, and it's 3D. And we can get the first reconstruction of the velocity. This is old. The data are almost 9 months old. We have not reprocessed more of them, but we have improved the reconstruction algorithm. So with the same image, our beam is fairly coarse, and by using some new tools that we learned from microscopy, the convolution tools, we can make the beam looks much thinner. So we have not fully reprocessed all the data. We are still doing through a lot of work of developing the algorithms to process this. This is really called computational imaging. So even though we're experimentalists, we have about 50,000 lines of code behind this, and keep adding to it and modifying it. So we are fighting with bugs all the time. We are we know that. So one last thing I want to show you, Chris Marks came early last year. I was donated this facility that belonged to either a national lab. It took 2 flatbed trucks to move it. We almost lost it to a scrapyard, so we managed to save it from the death. And we went to see it in the lab, and we got into a warehouse because my lab couldn't access it. And I was like, what are we going to do with that thing? So we were thinking, scratching our head, and we were like, you know what, let's revisit. And on a Tuesday, I started revisiting those laws for scaling of high Reynolds number facilities. I will skip all the theory in the interest of time. And I came up with a design for this. So currently here are the big pipes, long pipes that exist, 2 minutes, long pipes that exist in the world to do high Reynolds number turbulence. The biggest one is the one in gray here, which is the Princeton facility called the super pipe. And really, to have a large scale in separation in Reynolds number, you want to be on this axis. R plus is your Reynolds number if you want. And before, if people use hot wire in air with a sensing length of 100 micrometer using a 10:1 aspect ratio, they can resolve all the way to that corner. Okay. So that was inspiration for 9 million euros spent in Italy in an old aircraft factory of World War II, underground in the mountains, so the Allies could not bomb them. They could keep building their plane. So that's 115 meters long, test section, plus all the thing around. And now because we can do MTV in wire, we have the same argument on the Reynolds number, that doesn't change, but I can have 1 order of magnitude more refined in my length scale because I can do smaller measurements than before. And so that's what we decided to call this dashed line is us now. And I'm a big fan of Oscar Wilde. So we decided to call this the excess pipe for not extra small, but extra smooth. The pipe inside is like a mirror. The surface roughness is 100 nanometer. You see yourself inside. It's amazing. It's really a Navy gun put together, many of them put together, highly polished, electro-polished piece of art. And so this is, so we have this old facility, the pump sucked, I don't want to reuse it for a new facility, so I'm recycling it for this facility and some other components to save on cost. And we are building this new thing that is now 130 feet long, the whole length of the basement of the building. And so my lab has expanded quite a bit. We have this shake table here and this bundle that we do, that is full height PWR. We have the big suction tank we built with the NCSU. And soon this big pipe and maybe another big fluid very soon. So that's all I have. I'm going to put the conclusion here in the interest of time. MTV is pretty cool. It's a spectroscopic technique, so you can do more than just velocimetry. Here, what we're measuring is actually mass transfer. The dye we use is quenched. The fluorescence is stopped by dissolved oxygen. And so here, what we're measuring for the first time, this is water, this is air. We're measuring the transfer of gas from the air to the water. So you see this dark layer that is here, that's diffusion of air, of oxygen from the air phase into the liquid phase. And as the capillary wave travel, you see here the shape of the wall shear, the shear at your interface. It's never been measured before. That's holy grail of physical oceanography, we could argue, or even multi-phase flow in some cases. And we can see how the vortex being created below the trough of this wave entrance, renew the surface, entrance this layer, rich in oxygen into the bulk of the flow. So this is really one of the things you can do with MTV, and with a very fine pattern we can do, going very quickly. We use that to create some 3D reconstruction of surfaces. So we're printing this now in the water, and we're imaging from the gas phase, doing ray tracing in 3D. We can reconstruct the shape of that interface from scratch. So all of this, again, when we do experiments, I will stop here, I promise I'll stop talking, but for us in the lab is like 6 months designing experiments, a week taking data, and 6 months or plus writing codes and processing data. There is no commercially available software. This is all from scratch from the group in my lab. So there's a lot of programming that goes into doing experiments, surprisingly. That's all I have, and thank you.
Thank you very much, Professor Bardet. Very impressive talk, especially the last minute was very encouraging. Questions, please. We have a few minutes. Anyone?
A comment and a question. So a colleague of mine at the PhD student told me that if the project doesn't fall apart 30 minutes after you've taken your final data, you over-engineer. So sounds like you
well,
hit that one real well.
We break lasers because I don't design them, but so far my facilities we never had any catastrophic stuff in the past.
So you got the data at the end.
But I mean that facility wasn't my fault. Never work with civil engineers. That's the
My real weak question here is there any room for using gratings, laser gratings for the MTV?
I mean, this is pretty much so. I didn't put it here. So if you use gratings in the general sense, what you do is diffractive optics elements.
Yeah.
And so this is the new thing we're doing now. So the Talbot effect is nice. It gives us lots of flexibilities. DOEs, we have shitty lasers, high M square, so the wavefronts are not very nice. So it does a lot of speckle when you do your pattern with DOEs. For coming with a higher quality laser, we'll get a cleaner signal. So we worked out on DOEs. In some cases, that's what we do, but we lose in signal quality. Again, with a single mode laser, I think we will not lose.
Other questions?
What about the dissolved oxygen? Can you do that with anything else?
Yeah, of course.
Like what?
How much money do you have? I mean, one of the things we're doing is we're doing something very similar in a wall-mounted flow now with a heat transfer, right? So we have a dye, we integrate it smartly, that is sensitive to temperature. And so that's a new project we're starting now to measure temperature and velocity simultaneously. Again, at the smaller scale, that matters. That's the big thing, right? So we hope to get the holy grail, I think, in thermal hydraulics or in heat transfer in general, which is your U prime T prime algorithm. It has never been measured. And people have attempted it with PIV, but their scale is like enormous. They filter everything, and the way they do it they have a lot of optical aberration that prevent them from having anything reliable. We have a small tricks that have been hinted at through the presentation that will allow us to minimize all those optical aberration and get to higher resolution there. So that's a big effort we currently have, is to do the same measurements with the temperature. In the past, we have done the same measurements, just the peak, the fluorescence with a pH. So we could measure pH as well. We could combine it with a bit of work with MTV. A colleague of mine does that to measure electric field as well. So we could think of having the right dye and measuring your electric field near a wall, erosion or whatnot. With that, so there's a lot of things you're in the spectroscopy world, which is a very, very exciting world. And so I think there's a lot of things knobs you can turn to get new measurements.
Are there possible applications for clinoptic imaging using PIV?
Yeah, I mean, so there's a big group and good friend of mine, Brian Thoreau, at the chair of the Aerospace department at Auburn University, is really the first one to do plane optic imaging, plane optic 1.0 with PIV. A couple of groups in Asia, I think Korea, and one group in Korea, one group in China are doing it with the 1.0 approach as well with the micro PIV. But with the approach that we have here, we beat them in resolution. With a much simpler imager. So we have not done it with PIV. I keep telling my postdoc, because in PIV, I've got the commercially available software from LaVision to do the 3D reconstruction. Instead of us writing thousands of lines of codes and fixing bugs and losing our night or sleep, we could just press the button and trust the code. Unfortunately, we have been extremely busy and we didn't have time to do it yet, but that's a low-hanging fruit we need to get to. Yes. And here, what you will do is not a PIV, it's really a PTV, because you have such a high resolution, you will follow particle by particle. At the microscopy scale. At large scale, PIV works. At the microscopy scale, you're better off with PTV.
Any last moment questions? Did you see it? Was it quick enough? Okay, I think typically.
No.
Yeah, typically. Well, I think we're good on time to conclude. Let's thank Professor Bardet again. Maybe if anyone wants to kind of talk offline, maybe next 15 minutes or so.